Hello everyone, welcome back to another video lecture. Today we're taking a look at the fourth chapter of the Formal Logic Primer. In this chapter we're going to really look at three interrelated things. We're going to look at brackets and how those get used, well-formed formulas, which is just a term to pick out a correctly formulated statement, and multiple complex statements. So really we're building on what we've seen in chapter 3. So in chapter 3, we introduced the different operators and how we can use those to show the relationships between simple statements. I used the analogy, it's kind of like glue that holds them together, because we can use it to take two separate things and sort of put them together in a way that produces one new thing. And as we're going to see, by using brackets, we can string those together. So we can not only take two things and stick them together, we can take a third thing and a fourth thing and a fifth thing and stick them all together, even though the operators really only, either if they're negation, they affect just one thing, or for the other four operators, they only affect two things. But as we can see, we can link together not just simple statements, but we can actually link together other complex statements, so we can be showing the relationship between more than just two simple statements at a time. I'll give a warning here. We're going to go through this material today and try to present it clearly and fairly concisely. As we're doing chapters 5 and 6, which we've got scheduled in for 2 different days, part of what we're going to do there is learn what to actually do with the truth tables. Well, I'm actually going to walk through how to do this. So if what we did in chapter 3 and then here in chapter 4, which is just going to make what was going on in chapter 3 more complex. If you're still having some trouble understanding, and after you've looked through the material a couple of times, the videos for chapters 5 and 6, I'm going to spend some time just sort of sitting and going through and say, okay, well, here's this complex statement. Let's try to string this together with the right sorts of operators and the right sorts of brackets and that kind of thing. So I am going to spend some more time demonstrating how to actually do this and not just telling you how to do it in some future videos. Okay, so with that, let's get into it. So first, a well-formed formula, or a WFF, often called a WOOF, or could be a WIF. A well-formed formula, what's that? And we're going to see that we help use brackets to produce these sorts of things. Well, a WFF, or well-formed formula, is really just a statement that is formulated according to the syntactical rules of our formal language, our statement logic language. So syntax is really about the ordering of words and parts of sentences to produce a sentence with meaning. So just sticking with English, if I produce the sentence, Carl is making a video right now, that works, that's fine. If I say, is making Carl video right now, that doesn't work. Now Carl making is video now. I might have repeated myself. But there again, it doesn't work correctly. The rules governing syntax in a language like English or many other languages tells us what we're allowed to do and what we're not allowed to do in terms of how things get ordered. And they have to be ordered in the right way to produce meaning. Now, if you do know some other languages, you'll actually know that in some other languages, there's a lot more conjugation that happens with particular words, which tells you what they mean, and then you're less restricted than in English about how you can order those words. But a language like English is governed a lot by the rules of syntax. That is, the order that the words come in are really important for determining whether or not a string of words is meaningful. Do they really constitute a sentence? Are they just kind of a word salad where there's a lot of words thrown in and they're sort of tossed together and you say, well, I hope you know what that means, right? So try to avoid that. Try to get a good sense of the rules of syntax in English so you don't wind up with a situation where somebody reads your sentence and runs into something like grammatical ambiguity, if you remember that. Really, depending on how the sentence is strung together, can produce a kind of ambiguity that can be avoided if just the words are ordered somewhat differently. So in statement logic, all simple statements are already well-formed formulas. Just any simple statement on its own, P or Q or A or B or whatever, some simple statement that we represent by a letter, that's it. Just a simple statement letter on its own is fine. Right? There's really nothing more to do with it. That simple statement letter just represents some simple statement. The simple statement itself is a statement. It's capable of being true or false. We don't need anything else to make sense of it. Now, of course, if we're representing some natural language statement, it's going to have to be constructed according to the rules of the natural language. You know, the simple statement is Carl's making a video Monday morning. It's going to have to follow those rules of the natural language to make sense. But once we put it into statement logic, we just represent it with one letter, then it's fine. The simple statement on its own is WFF. Where things get trickier is when we come to complex statements. For a complex statement to be a well-formed formula, each operator must be clearly attached to its corresponding number of logical units. Now, I already mentioned this at the start of this video, and if you've gone through the chapter 3 material, you're going to remember this. Negation attaches to one logical unit. All the other operators, so the other 4 operators, need 2 logical units. So conjunction, disjunction, implication, and biconditional all connect 2 units. Now, those units can be just simple statements, but as we're going to see, they can also be other complex statements. What really matters is that each operator is connecting the right number of things, connecting or is attached to or is modifying, because of course negation doesn't really connect 2 things, it just modifies or gets attached to one thing to change what it means. And for the rest of them, we need to make sure that they're all attached to 2 other logical units that themselves are also formulated in the right kind of way. So we've got some rules that we're going to take a look at for this. This is all on page 40, so there are these 4 rules for forming a well-formed formula. So take a look at the material on page 40 and after that as well, but I've tried to incorporate that here along with some of the clarifications just for explanatory purposes. So the first rule, 2 logical units must be connected by a binary operator. So if we have 2 different logical units and we're trying to connect them together, they have to be connected by a binary operator. So look, you can't just have PQ, right? You can have P and Q. So if you have a simple statement, it just has to appear on its own. So if we have an argument, right, you could have a premise that just has one simple statement. If you want more than one simple statement in the same premise being represented in the same place, you're going to have to join them together somehow, such as P and Q. Now, P not Q is not allowed. Why? Because negation is a unary operator, that is, it only affects one thing. So it only affects the Q, it only affects what comes right after it. And so if we have P not Q, really what's going on here is that we have P, which is one logical unit. We've got not Q, which is another logical unit. The negation just affects the Q. And then they're just right on top of each other, but they can't do that. If you have 2 logical units, and logical units can just be simple statements, there has to be something that goes in the middle. There has to be an operator that connects them. Otherwise, they have to appear on different lines. You can't have them in a string. So that's the first rule. If you have 2 logical units, they must be connected by a binary operator. Second, 2 binary operators cannot follow each other, but a negation may come directly after any operator, though a negation may never be placed at the very end of a well-formed formula. So just a couple of examples there. P or not Q is a well-formed formula. Why? Well, the not only affects the Q, right? It only affects the one unit that comes right after it. The or, the disjunction, right? The V-looking symbol. What's that connecting? It has to connect 2 things. And in this case, it is. It connects P on the one side. So we've got P, there's one thing connected by it. We've got the disjunction in the middle. And then on the other side, we have not Q. So it's P or not Q is being connected. So what we're being told, because disjunction tells us at least one of the disjuncts is true, either P is true or not Q is true, or both P and not Q is true. Right? What could those mean? Just to try to put some example in there. Well, look, P, Carl is making a video right now. That's true. Not Q. Let's just have Q mean it's cloudy. So not Q means it's not cloudy. So in this case, P or not Q means either Carl is making a video right now, or it's not cloudy, or both, Carl is making a video right now and it's not cloudy. Right? Really, all it's saying is that it's not the case. We could retranslate it because the disjunction is true as long as at least one disjunct is true or both are true. So the only time it's false is if they're both false. So this disjunction would only be false if I'm not making a video right now, which I am, right? And if it was false that it's not cloudy, that's a double negation, so said normally, or that it really is cloudy. So this disjunction would be false if I weren't making a video or if it was cloudy. Right? I am making the video, so the disjunction is true. My window's closed, but I don't think it's cloudy, but it doesn't really matter. As long as I'm making the video, the disjunction is true. If we look past the comma, P negation, that's not a well-formed formula. A negation always has to have something that comes after it. Now, the negation itself can come after another operator, as we see. Right? You can have P or not Q, but you can't have just a not at the end of a well-formed formula. It has to have something after it, because that's what it's negating. So here's an example of something else you can't do. You can't have two binary operators in a row. You can't have P and or Q. Right? Doesn't work like that. It's just not a sensible thing to say. It doesn't have meaning in this kind of language. A couple other examples, right? P and not Q, that is allowed. The negation immediately follows the conjunction. Just like with the first example, P or not Q, P and not Q also works. What it's telling us is that P is true and not Q is true. Just sticking with the previous example, P, Carl is making a video, and not Q, it's not cloudy out. Now, P negation and Q, that's not allowed because the negation comes directly before a binary operator. But it can't do that. It can come after any operator, but it can't come directly before in this way. So if you have a binary operator, it has to be connecting two logical units, and there can't be a negation right before it. Right? But a negation can come before, as we're going to see, a simple statement at any time, which is really what's going on in these other examples where it works. Right? Once we introduce brackets, we're going to see we can also use it a little bit differently there as well. Lastly, not P, a double negation like that. This is allowed. Why? Because a negation may come directly after any operator, including another negation. So you can have not P. That's fine. Right? You could have, we're not going to see it, you could have a binary operator like and followed by two negations, and not. Now, I think it's useful for the way we write to use brackets to help clarify what is being operated on. This is what we're going to see brackets being used for. So in practice, I'm not generally going to write not in the way you see below there. Though technically there's nothing really wrong with doing that because the negation can come after any other operator. All right, third rule. An operator must connect the appropriate number of logical units. One for negation, two for all other operators. Right? So if you have a binary operator like and, or implication, or biconditional, you can't just have that connected to one logical unit. You can't have P and. You also can't have and Q. But you can have P and Q, right? You need something on either side of the and. Same for the rest of them. You can't have P or. You also can't have or Q. You can have P or Q, right? With the operator in the middle and then the two units it connects on either side. Because negation is a unary operator, it only affects one thing. You can just negate a simple statement and that forms a well-formed formula. That forms a complex statement. Not P is a complex statement for our purposes. And you can always negate any simple statement. Okay. Fourth rule. And this is what gets us into brackets. And as we're going to see, brackets are very helpful. They also make things more complex, but they help us deal with these more complex things. So rule 4, whatever is contained within brackets constitutes a logical unit. Whatever is contained within brackets must follow the 3 rules above. And when an operator comes directly before or after brackets, then it takes whatever is contained within the brackets as one of the logical units it connects. So as you see, this is really where brackets get introduced, and all of a sudden things are more complicated because you need to keep this in mind. In practice, this is much simpler than it seems, and in fact, this helps us follow the other rules as long as you start getting the sense about how this language allows you to form statements that are meaningful, complex statements that have multiple parts to them. So what's this going to look like in practice? Well, look, something like this. P and Q and R and S. Now, when I say it like that, it all just sort of runs together, but that is a well-formed formula. And if you take a look at it, what's going on in there? Well, we've got an and in the middle. So look at the middle and, right? Now, on either side of it are brackets, really parentheses, round brackets. I'm going to use the word brackets for both kinds, and we're going to see that we can use them sort of in two different ways just to help us get clear on what's going on. We've got that and in the middle. On either side of the and is material in brackets. Now, the material in the brackets, the P and Q on the one side, the R and S on the other side, that material has to follow the normal rules to form well-formed formulas, right? You can't have incomplete statements inside of brackets. But what we have here is that and in the middle, that conjunction, and it's connecting two other complex statements. It's connecting P and Q on the one side, which itself is a well-formed formula, P and Q, right? That's a statement that makes sense. That's a statement we're allowed to make. We then stick it in the round brackets. Now it's one of the logical units. The conjunction in the middle is connected, right? Rather than that conjunction just connecting simple statements, what we have are two instances where simple statements are connected. They're then put into brackets. They then act as a single logical unit that's being connected by the and in the middle. So what we have here is a statement that tells us, the statement overall, governed by the and in the middle, is saying it's both of the following statements are true. P and Q taken as one complex statement, and the statement R and S taken in a complex statement. So what's really going on here is that the conjunction in the middle is operating on the logical units beside it, and the brackets show us what the logical units are. So conjunction always has to have two logical units it connects, right? That's just how it works by its nature. It sits in the middle, and then there has to be something on either side. What's on either side could just be a simple statement, like in, say, P and Q, but we can also use conjunction or any of the other operators to connect complex statements. We put the complex statements into brackets precisely to see where the different statements are. It's a way of making sense of what we're doing. Just like using punctuation, say in English, using commas or periods or something like that, shows us where certain bits of information start and stop. It shows us what fits together. That's really what's happening. So as I mentioned, each of the conjuncts here, so now in this conjunction, right, we've got the overall conjunction, P and Q and R and S. The conjuncts of that conjunction are P and Q on the one hand and R and S on the other. Now, within each of those conjuncts is contained another conjunction. In the first one, we have P and Q. Within just that statement, P is a conjunct and Q is a conjunct. Taken together, the statement P and Q is one conjunct in the larger complex statement, P and Q and R and S. Similarly, R and S is its own statement. R is a conjunct and S is a conjunct. If we put them together in brackets the way we do here, it becomes one conjunct, right? That complex statement R and S becomes one of the conjuncts joined by the conjunction in the middle. Now, and we'll come back to this in a moment, when we have not coming outside of the brackets, it's negating what's inside of the brackets. So really, for all of the operators, when they come right before a set of brackets, or right after, as is the case with all of the binary operators, right? They'll come before and after something. If they're directly abutting brackets, then they are applying to or modifying all of the information contained within the brackets. Right? Everything that's in the brackets is now constituting one of the logical units that the operator is modifying or connecting. Okay, so I already talked about this a little bit. There's a difference between brackets and parentheses. Brackets are really the square ones. Parentheses are the round ones. Sometimes they're also called round brackets. Now, I'm just going to call them brackets for the sake of convenience. As we're going to see, the way we can use them is just to alternate between them as a way of trying to help clarify where complex statements start and stop. So I'll use round brackets or parentheses just as the default notation. If you learn statement logic somewhere else, often what they do is just use parentheses. So if you have a complex statement within a complex statement within a complex statement, you'll just have parenthesis, parenthesis, parenthesis. And then you have to sort of look to see where they open and close. What we'll do is try to alternate. We'll go round, then we'll go square, then we'll go round, then we'll go square if we've got nested things like that. So it's a little easier to see, oh, okay, we've got a round bracket and a square bracket opens, square bracket closes. So we'll just alternate like that. There's nothing wrong with just using parentheses all the time if you wanted the round brackets. So, an example like this, we've got if P then Q and not P, if not P then not Q. What we have here is really two different implication statements that are conjoined. So what's really being asserted in one line here is it's saying it's true that if P is true, then Q is true, and it's true that if not P is true, then not Q is true. All right? So we can formulate it in that kind of way. Now, this is where things get really complicated, and you're probably going to start hating me at least a little bit. As I was saying, we can alternate between round and square brackets or parentheses and brackets just to help show what a statement is actually trying to say if we have it all on one line. So look, the very first statement on the left, P and Q. We know that one now. That's just asserting both P and Q are true. The next one, P and Q and R. This is very similar to what we were looking at on the last slide. What's that one saying? Well, it's really saying what we have here is a conjunction within a conjunction. Q and R is a conjunction, and it asserts Q is true and R is true. Now those two together are stuck into parentheses or round brackets. Now they're acting as one logical unit within a larger conjunction. That larger conjunction has and in the middle. It connects two conjuncts. One conjunct, the one on the left, is just P, just the simple statement P. And then on the right, the other conjunct is the complex statement Q and R. So together, that second complex statement, P and Q and R, is asserting that it's true that P is true, and it's true that Q is true and R is true. So really, that's just telling us that P, Q, and R are all true. The next one over, P and Q and R and S. Now this is where the square brackets come in, and this is what I was talking about. So we've got P is one conjunct, and what's our other conjunction? Everything contained within the round brackets. And if you look in the round brackets, what do we have? There's a set of square brackets. Within the square brackets is another conjunction. So the square brackets just shows us there's a complex statement embedded within a complex statement, and then that larger complex statement, so we've got the small one, the larger one, and then that larger one forms with the P to create one long complex statement. P and everything in the round brackets, right? That's the overall complex statement. If we then look inside the round brackets, we have two statements going on in there, right? So what you're going to get when you've got brackets like this, you can nest statements within statements within statements. So the Q and R, right, that's our smallest statement inside of the round brackets. And it's formulated according to those first three rules. We have a binary operator, and it connects two things, in this case, just two simple statements. That works, right? That's allowed. Now, because it's in square brackets, and there's a conjunction right after it, the conjunction on the inside there, the one right before the S, it's taking what's on either side of it as conjuncts. That's the S on the right side. And then on the left side, it's taking everything in the square brackets, Q and R. When we then look at the parentheses, the round brackets, we've got the statement inside of there. We've got Q and R as one conjunct and S, right? We've got that conjunction. Within Q and R, it itself is a conjunction. It has Q and R as conjuncts. So we've got Q and R as conjuncts. That's one conjunction. Q and R is one conjunct. S is another one. There's another conjunction. That's all contained in the round brackets. And then everything in the round brackets connects to the conjunction in the middle with P as the other conjunct. So this statement is telling us that P is true and Q is true and R is true and S is true, because when there's a conjunction, it's just saying that each of the things being asserted here is true. If we move one over to the right, we have basically the same thing going on. It was just going on in the previous complex statement. I've just added in another value here, T. Now what we have are two conjunctions, right? If you just look at the right-hand side, we've got the round brackets. On the inside is a conjunction, governed by the operator in the middle, that conjunction. On either side, each conjunct in the square brackets is itself a conjunction, right? Within the square brackets, we have two complex statements. They're both formed properly. They're well-formed formulas. They formulate the two logical units that the conjunction in the round brackets conjoins, glues together. Then all of that material within the round brackets is one conjunct, which is being connected by the conjunction in the middle with P on the other side. If you look over at the far right now, I've just played around with P a little bit, right? Here's something else we can do. P and Q can be one of the conjuncts for the main complex statement. And then the other conjunct has embedded within it a conjunction within a conjunction. Now, just for the sake of explanatory purposes here, I've just stuck with conjunction to show you how brackets can be used to carve up different statements and to show how they hang together, right? So if you look at the far right one, P and Q is one conjunction on its own. Then we have R and S as a conjunction embedded within R and S and T on the other side. So ultimately, the truth conditions here are going to be the same for the far right one as from the one just before it, because they're both telling us that P is true and Q is true and R is true and S is true and T is true. But once we start using other operators and using brackets this way, we're going to see that the truth conditions start getting altered somewhat, because it's ultimately the truth conditions of the operators we were studying in chapter 3 always apply. The things that change are what those operators are linking together. So a conjunction is always connecting two conjuncts, but the conjuncts themselves can be really complicated statements in brackets. An implication statement is always connecting an antecedent and a consequent. They might be simple statements. They might be very complex statements in brackets, right? And so on and so forth. Okay, so just a little bit more on negations and how brackets work, and then other operators as well. So because negation is a unary operator, right, it just applies to one thing. That's just what it means for it to be a unary operator. It must come before a bracketed unit, and it negates the logical unit as a whole when it does so. So look, not P and Q really tells us that the conjunction P and Q, because that's what's in the brackets, is false. Now, I've just noticed that where I've got on this first line where I say, because negation is a unary operator, it must come before a bracketed unit. That's only the case if you're trying to modify the bracketed unit. So you can have a negation inside of a bracketed unit. You just can't have a bracketed unit with a negation afterwards, right? You can't have it at the end of a well-formed formula. It remains the case that a negation directly before a simple statement only negates that simple statement, even if that simple statement is part of a complex statement. So we can have this, right? Having inside of the brackets, P and not Q reads, it is true that P is true and Q is false. Or we could also say, and not Q is true, right? Saying not Q is true or saying Q is false, it's the same thing. It's logically equivalent, right? So you can have the negation inside of the brackets if it's following the rules and it's applying to, say, a single simple statement. You can also negate a complex statement by putting the complex statement into brackets and then negating the complex statement by putting the negation before it. You can't have bracketed material with a negation coming right after it. That's not allowed. So it can't come after a bracket. Brackets aren't themselves operators. They're just a kind of punctuation mark we use to show what the operators are actually operating on. Okay, just a few words about other operators. So the other operators always connect what comes before and after them, right? P and Q or R reads both because it's a conjunction, right? That's our main operator there. We've got P and Q or R are true. So what does that mean in practice? Well, because it's a conjunction, it's saying both conjuncts are true. When are both conjuncts true? Well, P is only true when P is true. That seems sort of obvious and stupid when I say it. The other conjunct, Q or R. Q or R is true when at least one of Q or R is true. It's also true when they're both true. So in this case, the conjunction P and Q or R is true when P is true and at least one of Q or R is true. Then this whole string, this whole complex statement is true. Right? We can switch it around. And this is where the brackets become really important. So you can't have just sort of a string of operators and simple statements in a row with no brackets, because then we're not really sure how to read it. But when you use the brackets, what you're doing is showing what are acting as disjuncts or conjuncts or the antecedent and consequent, what it is the operator is taking as the units it's modifying. So the second example, P or Q and R, now it's a disjunction is really the main, that's what the complex statement overall is. In the first instance, in the second point above there, it was a conjunction. It was P and Q or R. Right? So it was really a conjunction that was taking a complex statement as one conjunct. In this next example, we have a disjunction, which is taking a complex statement as one of the disjuncts. So here what we have is the disjunction, which is true as long as one of the disjuncts is true, or both. And it's telling us that either P is true, or Q and R, the conjunction of those two, is true, or both are true. So for this to be, for this complex statement to be true, it can be true as long as P is true on its own, Q and R are both true, right? Well, P is false. That would still be one disjunct being true. Or P is true while Q and R are also both true. Right? That's how we'd read that one. Now, here's an even more complicated one. We have a complex statement. Ultimately, it's a conjunct. It's governed by the conjunction in the middle, and it's taking as two conjuncts the material in brackets. The first complex statement that serves as a conjunct, the first logical unit, is the conjunction P and Q. The second one is another complex statement. So the second logical unit, the second conjunct being connected here, is the complex statement R, if and only if, not S. So what that's telling us, that second complex statement, it's saying either it's true that both R and not S are both true at the same time, or they're both false at the same time. Remember, that's what the biconditional tells us. So in one conjunct, we have that. Either R and not S are both true or false. That's really what the biconditional says. The other conjunct is saying both P and Q are true. The conjunction in the middle is asserting that both of those conjuncts is true. It's saying it's both true that P and Q is true on the one hand, and either R and not S are both true or both false. It's saying R is true if and only if not S is true, which means that if not S is false, namely that S is true, then R is also going to be false. I know that's starting to get pretty complicated. Like I said, this material does get complex fairly fast, but as long as you've been following along, you understand how the operators work, you've got a sense of how truth tables work. As we move through this material, especially as we look at chapters 5 and 6 and are actually practicing this and using the truth tables to test arguments for validity, you'll start seeing that there are underlying patterns that you can use, which, in effect, as long as you don't make a mistake in how you're filling in the table, we can take very complex information like this and do some pretty powerful things with it, checking arguments for validity or invalidity. So one more example here, P and Q, if P and Q, then R. So what's that saying? If the conjunction P and Q is true, namely if P and Q are both true, then R will have to be true as well. Here we have an implication statement. And the antecedent in this case is one complex statement that's serving as a single logical unit. All of the examples we have here over on the left are all well-formed formulas. They follow all the rules they need to. They're using brackets the right way. Operators are connected to the right number of logical units. Right? Each binary operator is connected to two things. Each unary operator, the negation before S, connects to one thing, not S. And of course, the negation can come right after any operator, right? And come right after the biconditional. You can't have two binary operators right after each other. So we can't have and, or, right? If. We can't have those things following right on top of each other. They have to be separated by brackets. And then it can be used, but of course, within the brackets still has to connect the right number of units as well. So as you see in practice, what this actually looks like is, generally speaking, what's going on in brackets. You've got, you might just have, say, a negation, which we could do. We could stick that in brackets all on its own if we wanted. I'm generally not doing that here and just letting the negation stand on its own. And then we get our brackets really closing off what would itself be a fine statement, Q or Q and R, or P and Q, or R if and only if not S, right? Those could all just be statements on their own line. They would make sense. They'd be well-formed formulas. But we can put them within the brackets. They can then serve as one of the logical units that another operator is working with. Okay, let's look at some complex statements. Now here again, you might not like me very much in doing this. Here's a big, complicated truth table. So we've got three different statement letters here. We have P, Q, and R. Right? So P, Q, and R. Now if we look at that truth table, because we have P, Q, and R, we've got three simple statements. We need 8 rows after the header row. So we've got a column for P, Q, and R, and we start with our simple statements having our own columns on the left of any table we make. In this case, we have P, Q, and R, and then we have to fill it in as usual. So that's going to be under our first simple statement, P, half true, half false. So the first half of the cells are true, the second half of the cells in the column are false, right? True, 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 false, 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 false. For the Q, we have the number that we're entering at a time. So true, true, false, false, true, true, false, false. And then ultimately, with our last simple statement, we always end up alternating true, false, true, false, true, false, true, false. Okay, so we're done all that. What are we going to do afterwards? Well, we need to make columns for each of the complex statements, right? What complex statements do we have? Well, we have to look within the brackets as well as the whole complex statement. So in that very first example, we have P and Q or R, right? So that statement as a whole will have a truth value. It's either true or false that P and Q or R is true. Now, to figure out whether or not P and Q or R is true, we need to know if Q or R is true on its own, because that's serving as one of the conjuncts. So we're going to separate out our complex statements and have a separate column for each one. That's really what's going on here. So I've got P, Q, and R as the simple statements. Then there's a separate column for Q and R, and a separate column for P and Q or R. That's my next two columns, really just representing this first statement. After that, the next complex statement we have, if you look at the examples on the left, are P or Q and R. To figure out if P or Q and R are true, we're going to need to know if Q and R is true, right? Because it serves as one of the disjuncts. So I've got a column there for Q and R. I also have a column for P and Q and R, or P or Q and R. Same thing for the last two columns. If you look at the last statement over on the left, we've got if P and Q, then R. So I've got a column for just P and Q, because we need to know if that statement's true. And then we have a separate column for if P and Q is true, then R is true. Now let's go ahead and take a moment and just work through some of these. So here again, I've just got a Word document that I'm using. I'm just going to be flipping back and forth here. So look, P and I'll zoom in a little bit, P and Q or R. This is our first statement. Let's just, so that other statement, it's a big monstrous one. You know, that truth table, I've just done all the work already there. But of course, you might look at that and just say, well, that doesn't help me. Okay, I see a whole bunch of T's and F's and a bunch of columns and a whole bunch of, you know, symbols and stuff. But how do I get there? How do I build it? This is where we go back to what we were already doing. This is where chapters 2 and 3 come in handy. And at least for now, I'm just dealing with everything symbolically. So in some sense, I've just forgotten the world, right? I'm not even trying to fill in what these letters represent. What are the simple statements? What is P and Q and R? Doesn't really matter. That's exactly the whole point of studying formal logic this way. Doesn't really matter what the statements themselves are. We're studying the relationships between them to see what sorts of relationships are truth-preserving and which ones aren't. Now, of course, when we're actually applying this to the world, we're going to want to know what those statements mean, because that'll help us determine whether or not certain statements, certain relations are true or false about the world we're in. But we can just focus on doing this for now, develop this tool, and then we can apply it later. So look, P and Q or R. So let's just take that statement and just try to construct a truth table to show whether or not that statement itself is true or false. So look at that. We've constructed this part of that long, big truth table we're looking at. We now see the truth conditions of P and Q or R. Now, we could take the time to do the same thing with those other statements. So just flipping back to what we're looking at. You can see the order's a little bit different, but on this big table, what do we have? We've got columns for P, Q, and R, the simple statements, and those are all filled in. We then have Q or R and P and Q or R, and that's going to be filled in the same way as we saw before. Now, Q and R and P and Q and R, those columns are in different orders between the two tables. Does it matter? Not really. It doesn't really matter. My suggestion generally is try to go from simple statements and then build your way up to the most complex statements so you can fill in the table as you're going along. Now, for this table that's on the screen right now, I haven't done that. Why? Because there's 3 different example complex statements, and I'm trying to show you the truth conditions of all of them here, right? So the first complex statement, P and Q or R, and the next 2 columns after the simple statements, there are the truth conditions for them, right? And the truth conditions of P and Q or R depend on the truth conditions of Q or R and P. The next complex statement over on the left that we're looking at, P or Q and R. So if you look back at the big table, I've put in what we need. We have Q and R. We then have P or Q and R. The last example is P and Q, right? If P and Q, then R. If you look at the big table, the final 2 columns on the right are P and Q, and then if P and Q, then R. Now I've put it all into this one big table. Why? Because the truth values for all of those complex statements ultimately depend on the truth values of the simple statements that make them up. All 3 complex statements, right, all the big strings of them, all have P, Q, and R as components. And so we've just got one big table here that shows us the possible combinations of the truth values of P, Q, and R. We then have the derivative truth values of all the complex statements that depend on those main truth values. Right? That's really what the rest of the table is showing us. So as we're going to see in chapter 5, when we actually use these tables to look at arguments, what we're going to do is make tables like this one. We're going to have one table that represents the whole argument. We'll have all the simple statements laid out, then all the complex statements in the argument beside it. We'll label the premises and the conclusion because it's going to matter at that point. And then we're going to read the rows to look for some specific information that tells us whether or not the argument is valid or invalid. So for the sake of time, I'm not going to work through producing the other 4 columns on this table here over my Word document. Try working it out yourself, though. This is a good exercise. So take these 3 sample statements over on the left, right, that I'm using here, without looking at this table. Of course, we've been working through this for some time now, right? Watch the video, sort of step away, write down those statements. See if you can reconstruct my truth table here. See if you can work through the steps of truth table formation to actually get all the truth values for P, Q, and R, and then if you can fill in the truth values for all the complex statements. If you can do that, you're on the right track. If you can't, don't worry too much yet. As I said, in the next couple of chapters, we're going to be doing more practice to see how all of this works, right? How to actually do it. But this is a good spot to take a little bit of a pause, see if you understand what's going on as we're dealing with more complex statements and how to formulate those, how to stick them on a truth table, how to read formulas that involve brackets. This is a good exercise. All right. Now, that ends section 4.1. How to use brackets, how to formulate complex statements with them, how to have a complex statement, one of the binary operators taking complex statements itself as the logical units it's connecting to make even more complex statements. Now we're going to talk for just a few moments about necessary and sufficient conditions. We already talked about this earlier in the course, but statement logic is very useful for representing these. There's some interesting overlap, and then we're also going to talk about the exclusive disjunction, but we'll get there in a minute. So talking first about sufficient conditions. An implication statement really just is a statement about sufficient conditions. Remember, a sufficient condition is really telling us that if one thing is true or happens, that's sufficient or enough for something else to be true or to happen. So if P then Q just tells us that if P is true, then Q is true, right? It says if P is true, Q must be true. That's really all it's trying to tell us. We can state that differently. That means the truth of P is a sufficient condition for the truth of Q. And if we look at the truth table, right, this was just the definitional truth table for an implication statement. If P is true, then Q is true. That means when P is true, Q must be true. It cannot be the case that P is true while Q is false. That really just means P is a sufficient condition for the truth of Q. If P is true, Q has to be true, right? Period. What happens if P is false? Well, Q could be true or false. And that's exactly what a sufficient condition is. A sufficient condition tells us something is enough for something else to happen or be true, but it doesn't tell us that it has to be there, right? It's not necessary. Of course, the same condition can be necessary and sufficient, right? Or necessary and jointly sufficient if there are multiple necessary conditions that together are sufficient. But a sufficient condition on its own is just saying, if this one thing's true, then something else is true as well. That's exactly what an implication statement already tells us. So, moving to necessary conditions. These require a little bit more ingenuity, but they can also be represented very well in statement logic. So, we can represent them in two different ways, because really what we're doing, if we say P is a necessary condition for Q, we're saying, and you can't have Q be true unless P is true, right? We can say that two different ways. One, we can flip around the implication statement. If P is a necessary condition for Q, that means if Q is true, right? If Q is the case, then P must be true as well. So think about it. If P is, it's cloudy, and Q is, it rains, right? What we're ultimately saying is that if it's raining, then it's cloudy, right? If it has to be cloudy for it to rain, then anytime it rains, it must be cloudy. It can't be true that it's raining unless it's cloudy, though it could be true that it's cloudy without it being raining. We can also express this as not P, if not P, then not Q, right? So if P is a necessary condition for Q, if P isn't true, then Q can't be true either. And we can stick this on a truth table, and here again, you're probably going to hate me a little bit, just to show the differences between them. Now we've got P and Q. Now, I still have P and Q in just their alphabetical order here. But if you look at that first statement, it's if Q then P, right? Well, that's fine. On our truth table, we can have P and Q, and we've got our true, true, false, false, true, false, true, false. Now that implication statement is if Q then P. An implication statement is only false when the antecedent is true and the consequent is false. Now we have to, in a sense, reverse our reading of the columns of P and Q in this case so that we're getting it right. And you're going to encounter this as you build truth tables. You're going to have a row where you have an implication statement, and there's no guarantee that the antecedent is going to be on column at the left and the consequent will be on column to the right. These can get turned around, where you can have the antecedent on the right and the consequent on the left. So to look at that third column, if Q then P, what do we have to do? Well, we have to read the truth values of P and Q, if Q then P is only false if Q is true and P is false. So we just look on the first row. Q is true and P is true. So the statement if Q then P is true. Second row, this is the one where if this statement was if P then Q, then the implication statement will be false because P is true but Q is false. But remember, our antecedent here is Q. Q is false. Anytime the antecedent is false, the implication statement is true. Right? It's just not telling us anything about the situation where Q is false. So if Q then P is true because Q is false in row 2. In row 3, Q is true, but P is false. The antecedent is true and the consequent is false. That means the statement, if Q is true, then P must be true as well, is false. So we put that in on the third row. And then in the final row, Q is false again, so the statement, if Q, then P is true. Now, we also have if not P, so this is the second example, then not Q. This is the second formulation. I've added on 3 other columns. There's a column for not P, a column for not Q, and a column for if not P, then not Q. Take a look at that last column, if not P, then not Q. I'm sure you can take a look at the values of not P and not Q, which themselves are determined by just reversing the values of P and Q. So whenever P is true in a row, not P is false. Whenever P is false, not P is true, and the same with not Q. We then fill in the truth value of the complex statement, if not P, then not Q, based on the values of not P and not Q. And if we then compare the truth values, right, the situations under which if Q then P is true, and if not P, then not Q is true, we see the same pattern. Under exactly the same situations, if Q then P is true, and if not P, then not Q is true, right? Those statements are logically equivalent. They're true and false under the same conditions. They're 2 ways of basically saying the same thing. So if we take this back to a necessary condition, right? A necessary condition is telling us that if one thing is a necessary condition for another thing, the second thing can't be true unless the first thing is true as well. This is really what we're hearing, right? If P is a necessary condition for Q, right? If it has to be cloudy for it to rain, right? So P is it is cloudy, Q is it rains. We can represent that 2 ways. We can say formulation 1, if it's raining, then it's cloudy, right? Or if it's not cloudy, then it can't rain, right? If it's false that it's cloudy, then it's false that it is raining. Those would be formulations 1 and 2. And you can see the truth conditions on the truth table. Now, hopefully that still makes sense. One other thing to point out is that this all amounts to basically a biconditional. Right? So we can string together what we already had. We can have, if we have sufficient and necessary conditions, or necessary and sufficient conditions, the 2 together, we can represent this with that complex statement at the start there, right? If P then Q, that's asserting that P is a necessary condition for Q. And if not P then not Q, that's telling us that P is, so if P then Q is telling us that P is a sufficient condition for Q. If not P then not Q is telling us that P is a necessary condition for Q. So that statement, if P then Q and if not P then not Q, is really telling us that P is both a sufficient and necessary condition for Q. That all amounts to a biconditional. A biconditional represents a sufficient and necessary condition together. And I'm going to go ahead and put that up on a truth table. So here again, you might hate me, but take a little bit of time, look over this table and think about what we've just been talking about. What's on the table? We've got columns for P and Q. We've got columns for not P and not Q. We have columns for the implication statement. If P then Q, if not P then Q. We then also have a column for the larger complex statement that takes those 2 implication statements themselves as conjuncts. So we've got the conjunction, if P then Q and if not P then not Q. that conjunction is asserting that both of those implication statements are true. And if you look at the truth values in the columns 4 and 5 for the implication statements on their own, you see that the conjunction is only true in the first and fourth rows. A biconditional, P if and only if Q, is only true if both P and Q are true or if they're both false. As you'll see from looking back in the rows for P and Q, the biconditional is true in the first and last rows. So the biconditional is true in the same situations that these two implication statements, if P then Q and if not P then not Q, are true. So a biconditional really amounts to two implication statements. Only two implication statements when they're formed in the right sort of way, namely this way. And of course, we could substitute out if P then not Q for if Q then P, because those are logically equivalent as well. They're just saying the same thing. Ultimately, they have the same truth conditions. So there's no logical difference in how they operate. Okay, I hope that all made sense. Now, looking at 4.3, this will be our sort of last real part to chapter 4 here to talk through. Exclusive disjunction. So we noted that the disjunction as it's normally used in statement logic is inclusive. That is, we say either this is true or that is true, and included as a possibility is that they're both true. The exclusive disjunction tries to deny that. The exclusive disjunction, which you encounter in daily life, says either this is true or that is true, and we exclude the possibility that this and that are true, right? It can't be both. We can represent that using the tools we already have at our disposal. This conjunction here produces an exclusive disjunction. We have as one disjunct, or as one conjunct on the left-hand side, P or Q, right? That's just a normal inclusive disjunction that says either P is true or Q is true, or both P and Q are true. That's one conjunct. That's our leftmost conjunct. We then have the conjunction in the middle. Right after the conjunction is a negation. I put a little space here just to show we've got the conjunction in the middle. It's taking that disjunction on the left as the first conjunct, conjunction in the middle, the operator, and then we have a conjunction as the other conjunct, right? So the conjunction in the middle, to the right of it is this bracketed conjunction, but outside of the brackets is a negation. Now, the negation can come right after the other operator, so we can have and not. The not then negates everything in the brackets. So what it's saying is that this overall conjunction is asserting it's both true that P or Q is true, one of P or Q is true, or both is true, and it's false that P and Q are both true. Right? We're negating the conjunction. We're saying it's not the case that P and Q are both true at the same time. So we can put that on a truth table. Take a look. We only have P and Q. Those are two simple statements, so that's all we have to deal with. So we only need 4 rows. But we need some extra columns. We have a column for P or Q, because that showed up in that complex statement. We have a column for P and Q, because that showed up in the complex statement. We have a separate column for the negation of P and Q. Do we really need that? Again, you could do it in your head, but I'm going to ask you to actually put the column in. Why? Well, because the negation of P and Q is just really reversing the truth values. So as you see in those columns, in columns 3 and 4, in column 3, P and Q is true, false, false, false. In column, so that's column 4. Column 5, not P and Q. There we have the value false, true, true, true. Whenever P and Q is true, not P and Q is false, and vice versa. Finally, in the last column, to figure out whether or not the conjunction there is true, we have to look back to the columns that represent our two conjuncts. The first conjunct is P or Q. That's represented in column 3. The second conjunct is not P and Q, which we see represented in column 5. And the reason we have column 4 is to help tell us the truth values contained in column 5. So together we take the truth values of column 3 and column 5. We then look to our conjunction. Our conjunction is only true when both conjuncts are true. And we only see that in rows 2 and 3. If you look back to the simple statements, P and Q, what this big complex statement in the last column is telling us is really just that either P is true or Q is true, and it's not the case that both P and Q are true together. That's just what an exclusive disjunction means in natural language, and we can represent it symbolically here with just a little bit of work. Now, of course, this is a little bit cumbersome. This seems a little bit more difficult than explaining in natural language what we mean, but not really. Because if you really press somebody and they say, oh, you can have this or that, if you really want to know what they mean, you need to press them and say, do you mean I can have this and that, this or that, and both this and that? Or do you just mean I can have this and that, but not both this and that? That's what we're doing symbolically. So in a way, doing it symbolically, although you have to do some work to get everything into the symbols to start with, once you're here and once you're working with it, this is actually a very efficient way to start representing the relationships between statements, which tells you about their truth conditions. And ultimately, it's the truth conditions we're interested in when figuring out whether or not a deductive argument works properly. That is, whether or not it's formally valid or formally invalid, whether or not it's truth-preserving or not. That's exactly what we're going to see in Chapter 5. So that takes us through the material in Chapter 4 that we need to take a look at. Like I said, this material is tricky. It's taking the material from Chapter 2 and 3 and making it even more complex. If this doesn't make sense, I encourage you to watch the video again, do the reading again, do the practice questions at the end of Chapter 4. Try to even work through what truth tables I've put up here. See if you can construct them. Going back to Chapter 2 and Chapter 3, drawing on the rules of truth table construction. Just ignore premises and conclusions for now. We weren't looking at arguments, we're just looking at how to put complex material on truth tables. So look at how to form a truth table in Chapter 2, take the truth conditions for the various operators in Chapter 3, introduce brackets, and you'll have the tools at your disposal to make these more complex truth tables. And in the videos for Chapters 5 and 6, I'm going to be doing some more practice, working through some problems, showing how we construct these complex statements, how we form our truth table, and then ultimately how we read the truth table to see whether or not an argument that we're examining is valid or invalid. So thank you very much. I hope everything in here was as clear as possible. I hope you're having a fine day, and I'll be back this coming Wednesday with another video. Bye for now.